Okay, so we will examine a problem that we have done before using Newton's second law for regular second law for linear kind of motion, right? F equals ma. However, we never considered massive pulleys. We always said that the pulley was massless and frictionless, and the rope was massless. The rope here for that is connecting the two masses of massive boxes, 12 kilograms and 11 kilograms, is massless again. However, the pulley in this case has a mass. Okay. So what is the consequence of the pulley having a mass? We'll see shortly. But first of all, since this is a similar problem to our to just application of Newton's law, Newton's second law is actually the same problem, a little different. We will start by drawing free body diagrams because that is our approach to solving Newton's law problems. For the 11 kilogram box, what do we have? Let's consider downward to be positive y, since the acceleration of the boxes will be as such, and the free body diagram for the 11 kilogram box will look like it will have a weight 11 times g going down, and the tension will be pulling it up, and let's call this tension T1. For the box on the table, we choose positive x in the direction of the acceleration and positive y as normal up, and the free body diagram looks like this. It will have a weight of 12 times g and a normal force because it is in contact with the table, and the rope will pull on it with a tension force T2. This is the consequence of having a massive pulley. For a massive pulley, the tension on either side of the pulley will be different. Therefore, we labeled it as T1 and T2. Why will they be different? Well, let's look at the pulley now. The pulley is a badly drawn circle like that, and the two ropes go over it. One rope is going this way, the other is going that way, right? And in what direction is the force on the pulley being applied by these ropes? The ropes will always pull, right? So this horizontal rope pulls in this direction, and that is the rope connecting it to the 12 kilogram box. So the tension in this rope is T2, while the tension in this rope connecting the 11 kilogram box is T1. Why are they different, the tensions? Because the pulley must rotate, right? And we take counterclockwise to be the positive direction of rotation. For this to rotate, it needs to have a net torque, right? The torque cannot be zero, the net torque cannot be zero for it to have a rotation. For that to be true, there must be an unbalanced or unequal force on either side causing this net torque. Therefore, the two tensions must be different. Otherwise, it wouldn't make sense. The pulley wouldn't go anywhere if the tensions were the same. The forces would produce the exact same amount of torque, and they would cancel out. The radius is 0.2 as given to us, and the weight of the pulley doesn't really matter to us because the pulley is not moving in the vertical direction at all. It is rotating, and we only consider the rotational force. And you can think of the weight as, of course, the weight acts always through the center of mass, and the center of mass in this case is the center. So if you have a weight going this way and the pulley is rotating about a fixed axis at the center, then remembering what the definition of torque was, F perpendicular times R, the perpendicular component of the force times the distance away from the perpendicular component application point to the fixed axis position R, then there is no distance away from the fixed axis position, right? The force is applied at the fixed axis, so no torque will be resulting from this 5 times g. So the weight we can just ignore, plain and simple. Alright, the next step obviously is to is to write down Newton's second law for each of these objects right here. So for 11 kilogram box, the motion is only in the y direction, so Fy is equal to may, and let's call ay to be just a meaning the acceleration of the whole system will be, since they are connected, they will be the same. So what are the y forces? We have 11g in the positive y direction minus t1 equal to mass is 11 times a. Let's call this equation 1. Now for the 12 kilogram box, we have two directions, x and y. In the x direction, the only force is T2 in the positive x direction, and that is equal to the mass 12 times acceleration in the x direction, which is a. Right? Let's call this equation 2. And in the y direction, what do we have? In the y direction, the summation of the forces is equal to 0 because the forces are balanced since the box is not accelerating up and down. So in the y direction, the normal force is just equal to 12g. The forces are balanced in that specific direction. No problem there. For the pulley, we have to use the alternate Newton's second law, that is the Newton's second law for rotations. Why? Because the pulley is rotating. It's not moving either horizontally or vertically. Since the rotation involved, the Newton's second law changes as follows. Now, the summation of torques. What are the forces causing a torque on this? T2 and T1. T2 will pull along this direction, and if you fix your axis to be the center of mass, then it will cause a clockwise direction. Actually, this is not positive. We have chosen counterclockwise to be positive. Okay. So T2 will be exerting a clockwise torque, while T1 will be producing a torque about x in the counterclockwise direction. Alright? So counterclockwise is positive, so the torque produced by T1 is positive. So T1 and the perpendicular distance is 0.2 from the center. So T1 times 0.2 minus T2, which is clockwise torque. So T2 times 0.2 equal to I alpha. What is I for the pulley? I is just that of a solid disk because it looks like a disk, and our fixed axis of rotation is at the center of mass, so we can directly read this off from the table of moment of inertia, which is 1/2 m r square. I is 1/2, the mass is 5 kilograms times 0.2 square times alpha. Alright, and at all of these terms at least have one factor of 0.2, so we can divide those out, and we end up with the equation T1 minus T2 equal to 1/2 alpha. Alright, let's call this equation 4. Now let's look at the pulley a little bit more closely. So if you have the pulley like this, and you consider the rope to be moving with the pulley rotates, right? And so the distance the pulley rotates must be related to the distance the rope goes. Hence, if you consider, let's use a different color. If you consider 2 points or 1 point moving on the pulley, say this point here, and it moves from here to there. It covers an arc length of a circular point, right? From the center, we see that this is just the arc length. The point moves an arc length of a circle, making an angle theta with the center. That means that this is the point through which the rope goes as the pulley rotates, right? This is the distance the rope travels as the pulley rotates, and the distance traveled by the rope is dependent on this angle theta, and we know how. The arc length, or the distance of the rope, is equal to the radius of the pulley times the angular displacement or position of the pulley. This tells me that there is a relation between angular and linear distance. Therefore, there must be a relation between angular and linear acceleration, right? And we know that to be true. If we look at the ropes, the rope is always moving tangent to the pulley, right? So the acceleration produced of the system is always tangential. And we know what tangential acceleration is. Tangential acceleration is related to angular acceleration as at equals r times alpha. At in our case is just a. R is the radius of the pulley, which is 0.2 times alpha, the angular acceleration of the pulley. Okay? Now our job is to use this information to simplify our equations. Let's go ahead and do that. Now we see that a is related to alpha. So since our final goal is to find a, we want to get rid of any alpha we see. So first we meet alpha in equation 4. So we can get rid of alpha by using this information. How? From this we can see that alpha is nothing but a over 0.2. Okay? So anywhere you see alpha, you can replace alpha by a over 0.2. Therefore equation 4 becomes T1 minus T2 equals 1/2 times a over 0.2. This is then T1 minus T2 equal to 2.5 times a. From here we can make a little bit more substitution, because we also want to get rid of, in addition to alpha, we also want to get rid of these tensions, because our goal is to find acceleration, not tension. So from this equation, let us choose to eliminate T2. So we can do that by adding T2 to both sides of the equation, and T2 becomes T1 minus 2.5a. Alright? And this is, let's call it equation 5. Alright? Now what? And then we look at other equations that we have. Equation 2 tells us that T2 is just 12a. Alright, so equation 2 and equation 5 are giving me the same variable using two different expressions. So let's keep that in mind. And then equation 1 has a variable T1 that we want to eliminate, right? We don't want tensions in our equations. So how do we do that? Well, we can just rearrange equation 1 as by adding T1 to both sides of the equation, and we get, on one side we get T1, and that is equal to 11g minus 11a. Let's call this equation 6. Alright? Therefore, we can now see that we have two equations, actually three equations including equation 2, where we only have acceleration a and no tension, either T1 or T2. So our next goal would be to plug equations one by one. So first of all, let us plug two similar things together. So 5 and equation 2 give me the same thing. So they both give me T2. So they're just equal quantities with two different expressions. So equation 5 equal to equation 2 gives T2. In place of T2 we can write T1 minus 2.5a equal to, the right hand side of equation 2 is just 12a. Therefore T1 is equal to 12a plus 2.5a, which is just 14.5a. Alright, let's call this equation 7. We can take this equation 7 and recognize that equation 6 gives me a different expression for the same thing, T1. So we can plug equation 7 in equation 6. This leads to, in place of T1, write 14.5a and set that equal to 11g minus 11a. A is an unknown here. Let's take a on one side. So 14.5a plus 11a equal to 11g. To get a, let's add the two quantities right here. 14.5 plus 11 gives me 25.5a equal to 11 times 9.8. Then A is just found by dividing both sides by 25.5, and we get an acceleration of 4.2 meters per second squared. So as you can see, this is just a load of uh, clever algebra to get to the answer. However, if you can set the problem up right, then the algebra is just a matter of plugging and chugging. I hope this more advanced problem of a massive pulley causing rotations and moving systems is a little bit clearer. Thank you.